everybody, welcome to the 5.3 notes. 5.3 notes are about determining intervals on which a function, f of x, is increasing or decreasing. And so the last notes we had, we were talking about critical points. And so here are some 3 reasons why we need to know critical points. We didn't talk about this in the last notes, but these are why they are important. Number 1, we can use them to determine intervals on which a function is increasing or decreasing algebraically, which is what we're doing today. Number 2, we can use them to determine where there is extrema on our function algebraically, so that's what we'll do later this week. And then number 3, we'll figure out characteristics of the original function if given its derivative. So basically, critical points help us figure out what's happening on the original function. So here is our key idea 1, and I'm going to put it in notation first, and then I'll tell you what it means in words. So it's already in notation. So this says in notation, when f prime of x is greater than 0, f of x is increasing. So right here it should go increasing. So when f prime of x, the derivative, so when the derivative is increasing, when the derivative is greater than 0, f of x is increasing. And this function right here is the original function. So, in words, what this means is when the derivative is positive, the original function is increasing. So, let's just take a second and kind of brainstorm, why does this happen? So let's first look at this function real quick, and I'm going to highlight on this function where it's increasing. It's increasing from here to here, and it's increasing from here to here. So that's where this function is increasing, where it's going up. So if I were to take, and I were to draw a tangent line anywhere on this function, I'm going to draw a tangent line here. I'll draw a tangent line here. Sorry, that one was a bad tangent line, but you get the idea. Tangent line, tangent line. If I were to draw a tangent line on any of the parts of the function where it is increasing, one thing that you might notice is that all of the tangent lines have slopes that are positive. And remember, the slope of a tangent line is the derivative. So all of the derivatives at every point here, they're all positive. And so if you do that enough and you completely do it, you'll realize that anywhere the function is increasing, that means the derivative is positive. And it works the same way, vice versa. So over here it says when f prime of x is less than 0, f of x is decreasing. And so in other words, what that means is that when the derivative is negative, the original function is decreasing. So if you look at that one section I haven't highlighted yet, so I'm going to highlight the new section. This section right here is decreasing, and any tangent line I would draw on this section, the slope would be negative, which means the derivative is negative there. And so after we've done this so many times, people realize that these rules had to be true. Here is our other key idea. So the switch, and this is kind of similar to the idea of velocity, acceleration, position. So before I talk about this, kind of connect it to that part. So remember, position's the original function, and then velocity is the derivative of position. And when velocity switches from negative to positive, remember how it has to stop before it can do that. It has to pause before it can switch directions. So keep that concept in mind when I talk about this right here. So the switch from increasing to decreasing must occur at an extrema. So if you guys look, and then this is just like the regular graph, okay? And this is something, this first concept right here, this first concept is something that you would have learned in like Algebra 2 or Pre-Calc. All of the places where it's switching from increasing to decreasing, so here it's switching from increasing, now it's decreasing, and then it's going to go and it's going to start increasing again, okay? The switch happened at a relative max, and then this switch happened at a relative min. And if you guys remember what we talked about yesterday is that any extrema shows up. Another thing that you could call an extrema is a critical point. So all extrema, what we talked about yesterday, is all extrema occur at critical points. And so the switch from increasing to decreasing must occur at an extrema and thus a critical point. And so therefore, The derivative switching from positive to negative must also occur at a critical point. So if the switch from increasing to decreasing must occur at extrema, then the derivative switching from positive to negative, that would also be a critical point. So we're going to go on to our next page. So all of this stuff like that we're just talking about, like we can obviously tell when original function is switching from increasing to decreasing, right? We can obviously tell the extrema of a function just by looking at the graph. So why is it important to figure this out? So sometimes we are given an algebraic representation of a function and unable to graph it easily. And if we want to figure out where the function is increasing and decreasing, we can use the combination of a derivative and critical points to figure it out. Math is fun. So here are our steps to figuring out whether a function is increasing or decreasing. And this is like very much an algebraic process, but this can also be used if you're given like the derivative graph and not the original function. So here are our steps to figuring out whether a function is increasing or decreasing. Take the derivative of the function. So you're always going to start by taking the derivative, and sometimes you'll get problems, and we can practice these in class, where you'll be just given the derivative. So either take the derivative or acknowledge the fact that you've been given the derivative. So I'm going to write or acknowledge that you have the derivative. Okay, so that is step one. Then what you'll do is find the critical points. Remember, the critical points are where the derivative either equals 0 or where the derivative doesn't exist. And then you're going to create a sign chart to figure out where the derivative is positive or negative. And think, this is what we did with velocity switching directions. So that was kind of the concept we used there. And then you have to state your conclusion. You have to tell me why. So those are our steps. So let's do our steps. So this says find where f of x equals x cubed minus 6x squared is increasing or decreasing. So again, obviously we could just graph this and we could figure it out, but we want to do this algebraically because I don't think you guys know exactly just by looking at the graph where it switches from increasing to decreasing, or sorry, by just looking at the equation. So my step one is I'm going to find the derivative. So to find the derivative, I will get 3x squared minus 12x. Pretty easy. So that was our step one. Step two is to find the critical points. So there aren't going to be any critical points because the function doesn't exist, because that is a quadratic. Everything works well with quadratics, but I can set it equal to 0 to see if I can find a critical point that way. This is a binomial, so since it's a binomial, what I'm going to start by doing is pulling out the greatest common factor, and both of those terms have a 3x, so I'll be left with x minus 4 when I factor that out, and I'll get 0 equals 3x, and 0 equals x minus 4, so I'll get x equals 0 divided by 3 is 0, x equals 4. So these are my two critical points. Step 3 is the fun part, so debatable whether you consider it fun or not. I'm going to create a sign chart. So this is where I know the critical points are occurring, but just because a critical point occurs doesn't necessarily mean we're switching from like increasing to decreasing or anything like that. So I'm going to start a sign chart. I'm going to do it actually over here so I have a little bit more space. And so I'm going to write down my critical points here. So if you imagine a derivative, right, I'm just going to imagine a function right here, okay, and we know that on our function, there's a point at 0, 0, and there's a point at 4, 0. So the reason I know that is because I know, like, based on this, that the y value is 0, and then these are the two x values. So technically, these are just like x-intercepts, right? So imagining this is why this sign chart works. In order for it to switch from positive to negative, it has to hit one of these critical points. So there's like a couple options of what this graph could look like, what the derivative graph could look like. So I'm sketching the derivative graph real quick. It could look like this, right? And so in this case, it would be switching from negative to negative, and therefore what the original graph would look like is it would look like decreasing, increasing, decreasing. The graph could also look something like this, though, and it could just like stop there. It could look something like this. So it could have a bounce. So in this situation, it would be switching from, the derivative graph would be switching from negative to positive, but then it would stay positive. So what the original graph would look like would be decreasing, positive, positive. And so essentially what we're trying to figure out is like, what does this graph look like? And so that is why we're doing this sign chart. We can't just like make assumptions. And so, but the big thing is the only time it could switch from positive to negative is it would have to go through these critical points. And so like it couldn't switch directions at 1 because there's not a critical point there. It doesn't go to 0 there. And so that's why the sign chart works the way that it does. So what I'm going to do, and this again is something that we did with velocity, is I'm going to choose an x value in these intervals. I'm going to choose an x value under 0, and I'm going to test whether it's positive or negative. I'm going to choose an interval between, or an x value between 0 and 3, test positive, negative, and so on and so on. And also, sorry, this should say 4, not 3. So let me fix that. So I'm just going to go ahead and start. So right here, I'm going to do -1. So I'm going to plug in -1, and I'm concerned about whether the derivative is positive or negative. And so I'm going to plug that into my equation, and I will get 3 times -1 squared minus 12 times -1. That equals 3 plus 12. I don't care what the number is, but I do care that it's positive. So anytime we are less than 0, we have just figured out, we don't know exactly what's happening, but we know that our equation is at least greater than 0. And so I don't know exactly what it looks like, but I know it's greater than 0. So now I'm going to go again, and I'm going to type in f prime of 1, because that's a number between 0 and 4. And I'll do 3 times 1 squared minus 12 times 1. That gives me 3 minus 12, and that's negative. And so I know that my derivative function is negative between 0 and 4. So if I go back over to my sketch, I don't know exactly what it's going to look like, but I know that it's negative. And then finally, I'll choose 5. F prime of 5 equals 3 times 5 squared minus 12 times 5. 5 squared is 25, so this is 75 minus 60, and that's positive. And so then this will become positive. And so this is just kind of a brief idea of like what the derivative sketch would look like. But what this tells us is, based on our rules, anywhere where the derivative, and this is where it gets confusing, you like really have to organize it well, but anywhere where the derivative is positive, so these two areas, what we would see on the original graph is the original graph would be increasing. And what I mean by positive is I mean the y value is greater than 0. So that's why these two sections are positive, right? So the y value here and the y values here are greater than 0. So on the original graph, we would see that this is increasing and this interval is increasing, and then this interval is decreasing. So my last step is to write my conclusions. And when I write my conclusions and I write these intervals, remember I'm doing them in x value. So I'm going to say that my function is increasing from, so it starts increasing in the negative. So it's increasing from negative infinity to 0 and 4 to infinity, because on those intervals, f prime of x is greater than 0. So that's one conclusion. And then I also know that it is decreasing. So, and the thing that is f of x. I can write that down. That helps. F of x is increasing. So f of x is decreasing from 0 to 4 because f prime of x is less than 0. And if you want to check your work, go ahead and graph this in Desmos, and you'll see that it really is increasing from negative infinity to 0 and 4 to infinity, and then 0 to 4. So that's the process. And we just need practice and just to kind of help you continue to hold this concept in your brain. So we're going to do 2 more examples. Feel free to try some of these examples on your own, though. Okay, here's our next example. Find where g of x equals the natural log of x squared plus 4x plus 4 is increasing/decreasing. So one thing to know, and this doesn't really impact this problem that much, but just so you know, the natural log is only defined between 0 and infinity. So like this could not equal a negative number. That would not be within the domain. So just keep that in mind, but we'll continue just like a side note. So I'm going to start by finding the derivative here because I need to figure out the critical points. So the derivative of this is the chain rule, inside function, outside function. So it'll be the natural log of x, or the natural log is 1 over x, so it'll be 1 over, and because of the chain rule, x squared plus 4x plus 14 times the derivative of the inside, which would be 2x plus 4. And to simplify that, I will get 2x plus 4 all over x squared plus 4x plus 14. So that's the derivative. Now we got to find the critical points. First way to find the critical points is where does the function, the derivative, not exist? So if I were to divide by 0, there would be an x value where this function doesn't exist. However, I'd like you to picture this function. This right here represents, so just picture the quadratic, like ignore 2x plus 4, just picture this part right here. 14 is a y-intercept. That's always represents the y-intercept, so that means that essentially like our graph is going to go through 14. And then this is pointing up because it's positive. So I don't know exactly where this graph starts, but it's pretty safe to assume that it's never going to equal 0 because it's like starting at 14 and then the slope is x, like it's like, well, not slope, but it's a positive a value. So I'm just going to assume that never equals 0 and I am correct. And if you didn't know if that was correct or not, you could graph it. So there's no critical point because the function doesn't exist. But there is potentially a critical point where the derivative equals 0. So I'm going to set this equal to 0. And I'm going to solve, so I'm going to multiply x squared plus 4x plus 14 on both sides. So cross off, I'll get 0 equals 2x plus 4. And that, if you solve that, you get x equals negative 1/2. So that is our critical point. So I'm going to do our little line test, sign test, and I'm going to write, oh wait, hold on, that's negative 2, my bad. I'm going to put negative 2 here, and I'm just going to do like a little sketch over here, down here on the graph, just to kind of help us out visualize this. So the sketch that I'm drawing is the derivative. So basically what we know is that at some point the derivative, well, we know that when x equals negative 2, the derivative equals 0. So that's what we know so far. And so now I'm going to do my sign test. So I'm going to plug in a number a little bit larger or smaller. So I'm going to plug in negative 3. And I'm going to plug it into the original function, not the simplified one. So I'm going to plug it into this guy right here. So 2 times negative 3, and you're welcome to use a calculator for this to make it go by quicker. So on the top, I'll get negative 2, and then it's 9 minus 12, 14. All I know is it's a positive number, and that's all I'm concerned about. So this is going to come out to be, it's going to come out to be negative because the numerator is negative and the denominator is positive. And then I'm going to plug in 0 instead of like 1 because 0 is just easier number worked with. So then on the numerator, I would get 4. I plugged in 0, and the denominator would get 14. That's positive. So based on the sign test, what we're learning is that the derivative is negative until negative 2, and then it's positive after negative 2. So that could be like a sketch of the derivative. And so that is what we figure out there. And so based on the sign test, our conclusion is that f of x, so all of this is helping us answer questions about the original function. So f of x is then increasing from negative 2 to infinity because f prime of x is greater than 0. And then f of x is decreasing from negative infinity to negative 2 because f prime of x is less than 0. So that is it. Okay, going on to the next page, and this is our last one. It's kind of getting cut off, but you understand what it's saying. So example 3, find where f of x equals negative x to the 5th power plus 5/2 x to the 4th power plus 40 x cubed plus 5 is increasing / decreasing. So same idea, start with the derivative. I'll get f prime of x equals negative 5x to the 4th power plus, if I drop down that 4, it'll end up being 10 if I simplify, because 4 times 5 is 20. 20 divided by 2 is 10. So 10x squared plus, if I drop down the 3, it'll cancel out the 3 in the denominator, so it'll be 40, and then the 5 goes away. So this one's looking a little uglier. It's a polynomial, so it will never be undefined. So now I'm going to start by pulling out the greatest common factor, which is 5 x, and then because the leading term is negative, I'm going to pull out a -5 too. It'll make our life like a little easier down the road. So I'm going to pull out -5x squared. So in the first term, x squared is left. In the second term, -2x is left. And in the third term, -8 is left. And then I will hopefully be able to factor that. So thinking about a is 1, so I can factor using like the easy method. So I'm thinking about what multiplies to -8 and adds to -2. That would be x plus x minus 4, x plus 2. And then I'm going to set all these terms equal to 0. So 0 equals -5x squared, x minus 4 equals 0, and x plus 2 equals 0. So I get 3 critical points, x equals 0, x equals 4, and x equals -2. So if I'm continuing to like want to give myself a little sketch just to help me visualize it, if this is our derivative, I would have a critical point -2, 0, and 4. And you obviously don't have to do that, but it kind of helps me a little bit. So we're going to do our line test over here to see where the derivative is negative and where is it positive. So I'm going to start over here plugging in -3, and I have to plug it in. I'm going to plug it into my most, like, you can plug it either into this one or this one. They're like, you haven't changed anything, you've just factored it. It's just in a different form. I kind of like plugging it into the factored form because I feel like it's like a little easier for me to do the multiplication. So I'm going to plug it into the factored form, but you could have used the unfactored form too, the standard form. So I'll have -5 times -3 squared, -3 minus 4, -3 plus 2. So I'll have I'm just going to kind of, I really am just concerned about like the sign. So it's going to be a negative times a positive times a negative times a negative. And so that will end up being a negative altogether. I'm going to plug in -1. I'll get -5 times -1 squared, 1 minus 4, 1 plus 2. So a negative times a positive times a negative times a positive, and that ends up being a positive. So far, if I go back down to my like sketch I was doing down here, I know that the graph is negative before, and then it's positive between these two numbers. So far, that's what I know. I'm going to plug in 1. F prime of 1 equals -5, 1 squared, which is a positive, negative, positive. So that ends up being a positive again. And then finally, F prime of 5, I'm going to plug in negative, positive, positive, positive. So it's a negative. So from that, I see that my graph actually kind of, like if you were to look at the sketch, it looks almost like this. And it obviously doesn't look exactly like that, but it stays positive for 2 intervals. And so my conclusion here is that f of x is increasing from -2 to 4 because f prime of x is greater than 0, and then f of x is decreasing from -infinity to -2 and 4 to infinity because f prime of x is less than 0. And that should be it. So enjoy these notes. Let me know if you have any questions.